So I want to thank everyone for joining us today. Semiconductors have been an issue that have been in the news a lot lately. The White House, Congress, industry groups have all identified these as a top priority for US innovation. They've also identified this as an issue where manufacturing capacity within the US is a bit of an issue right now that we need to address. There's a shortage of chips as we see increased production of devices that require them, and there are questions about supply chain security. So this is something that NSF, National Science Foundation, has looked at for years, and we've supported research that has examined semiconductors at every step of the way, from manufacturing, supply chain security, to the innovations that are going to build the foundation for semiconductor science in the coming 10, 20, 30 years. And to talk about that and to give the reporters on the call some good background, hopefully some good sourcing for future stories, we have an absolutely great panel, and we're going to, I'm going to introduce them now. We're going to go through some discussion with them, and then we're going to open it up to questions. So on our panel, and this list is in everybody's invitation if you need name spellings and affiliations. We have Dawn Tilbury. She is NSF's Assistant Director for our Engineering Directorate. Margaret Martinosi, she's NSF's Assistant Director for our Computer and Information Science and Engineering Directorate. And Thomas Kuch, he's a program manager who focuses on semiconductors and microelectronics. Tom, I should have double checked your last name pronunciation, so please correct me later if I got that wrong. We also have April Brown from Duke University, Daniel Holcomb from UMass Amherst, Malika Jeffries-L from Boston University, Joan Redwing from Pennsylvania State, and Subhashish Mitra from Stanford University. And so with that, I'm going to turn our attention to our NSF panelists first, and I'm just going to ask them if Dawn, Margaret, Tom, I was hoping you could frame this issue for us. I'm going to start with Dawn, and could you talk about the sort of broad manufacturing and fabrication picture here?
Oh, thanks, Rob. So I like to think about semiconductors as being the foundation for all of the industries of tomorrow, from artificial intelligence, algorithms that run on semiconductors, through advanced manufacturing of all processes, as well as the manufacturing of semiconductors. Also wireless, biotechnology, and quantum information science. All of these industries rely on semiconductor-based devices, platforms, and systems. So NSF supports basic research in future semiconductor technologies, from advanced materials and materials processing methods to new nanomanufacturing and chip manufacturing methods, designs, architectures, and techniques for integrating semiconductors into systems, including systems on a chip and photonic and quantum devices and systems. NSF takes an all-of-science approach, including basic materials, advanced and future manufacturing, user needs and interfaces, as well as education and workforce development, all the way from lab technicians up to PhDs. So some of the key aspects that NSF is investing in for semiconductors includes energy efficiency, security, and heterogeneous integration, including microelectromechanical systems, nanoelectromechanical systems, microfluidics, communications, and biosensing. The challenges with integrating all of these things into a chip can lead to more efficiency, but there are significant research challenges to make those integrations, especially in the manufacturing processes. So the investments that NSF is making in semiconductors are really leading to the next generation of electronics for both computing and communications, enabling us to build the industries of tomorrow. Thank you. Margaret?
Thanks, Dawn, and good morning, everyone. It's wonderful to be here to be able to talk about such an important topic. So I'm Margaret Martinosi, and I lead, as was said, the Computer and Information Science and Engineering, or SCIES, Directorate here at NSF. And I serve on this role while being on loan from Princeton University, where I'm a computer science faculty member. And in fact, my own research has long focused on computer system design issues, including architecting computing to be more secure, reliable, and power efficient. And so I speak for my field, for all of NSF, and from my own personal experience, talking about the way the ability to consider long-term semiconductor technology trends in such research has always been centrally important, as is the ability to test one's research ideas through access to semiconductor fabrication facilities by which to make prototypes. When we in SIZE speak about the future of our field, we talk about it in terms of 3 organizational themes. And one of those themes is very central to what we're talking about here today, namely the seismic shift we're seeing as Moore's law scaling slows and ends. So Moore's law was first articulated, as many of you know, by Gordon Moore, an Intel executive in the 1960s, to predict that transistor counts on chip could be cost effectively doubled every 18 months or so. And what's remarkable is that from the 1960s to nearly the present, the industry has sustained that exponential doubling for over 50 years. But as many of you know, Moore's law scaling now is slowing, and with each year it becomes harder, more expensive, and more technically challenging to achieve that kind of scaling. And as that happens, it's reshaping the layers that sit on top of that. It's reshaping all aspects of computer systems design processes. We're also seeing related challenges around enabling researchers to gain access to cutting-edge fabrication facilities for their work. So building advanced semiconductor and microelectronic systems today is definitely a technology and a circuits challenge, but I also want to stress that beyond that, this is really an all-hands-on-deck moment and opportunity for computing as a role. As the slowing of Moore's law scaling challenges our computing designs, we're seeing big opportunities, big changes already in how our phones and laptops are implemented, and this dramatically impacts software layers that sit on top of it. Within NSF, we're happy to be funding where we can cross-layer research that looks at how software researchers and hardware researchers can take on these problems together. And we're also looking at large-scale research in which these challenges impact AI, advanced wireless, and so forth. I'm really grateful to the NSF-funded researchers who've come here today to discuss more ideas and opportunities as we look forward on these issues. Thanks very much.
Tom, can you take us through some of the activities that we've looked at so far and what we're looking at in the future?
Certainly, and I would like to highlight a few things. First of all, I'm in the advanced manufacturing area of the Civil Mechanical and Manufacturing Innovations Division of NSF. Our cluster, our area, really looks at new advances in new science that goes into processing new materials. Semiconductor technology in history has been built upon several things. One, it's the innovations in new materials that led to innovations in new ways to process and manufacture these materials, that led to new ideas and devices, that led to innovations and advances in sensing, computing, biomedical applications, communications. So there is a vertical structure to this ecosystem where we start with materials, learn how to manufacture them at cost and with reliability and high efficiency, and then use these materials in a wide variety of ways. They're building blocks, they become bricks that are used to make all sorts of new devices. And I think you'll hear about new materials and new devices today. Our area then really looks at how we take these processes and push them forward. As we move into the next generation or next era of semiconductors and electronics, manufacturing is going to be key. The integration of artificial intelligence, machine learning, and other types of new processing innovations are going to be crucial. And NSF is funding research in these areas along with the new materials. One of the things that we do directly is that we solicit input from the stakeholders. These stakeholders are people who are researchers at universities, small companies, large companies, government labs. And we do this through a process of usually typically holding workshops. And these workshops have been going on. We have just finished a series of Future of Semiconductor workshops that will have reports that will be available eventually that look at the challenges in both, in the entire ecosystem, starting from materials up through how do we actually get access to, for researchers to actually use these materials, make devices, and at the highest level, as was just mentioned. And so these workshops have been going on and will be ongoing. Thank you.
Great. Great. And so I'm going to turn to our guests right now, and I'm going to introduce them and ask them to describe their work just a little bit. One thing I should note is when we're putting this panel together at NSF, we asked our staff to send us some great researchers, and we had way too many for one panel. So reporters logging in will also be sending you an information sheet with a whole dozens of researchers whose work you may be interested in. But I'm going to start us off right now with April Brown from Duke University. Can you talk to us a little bit about your work and the big issues you're focusing on right now?
Sure, and thank you. Good morning. I'm happy to be here. I hope y'all are doing well. It's an exciting time for people who have been engaged in research in semiconductor materials and devices. And it's great that Rob pointed out the difference. I would like to point out one thing is the need to have convergence in that research. Context for me or background is I've been involved in device and materials research for over 30 years at universities, government, and industry. What's exciting about right now, what's happening right now, and my focus through NSF funding is understanding how to advance manufacturing of new materials and devices for quantum applications. That's quantum computing, sensing, and communications. So there's lots of opportunity. It builds on our expertise. And it also, I think, engages the enthusiasm of students. So I'm going to stop right there. I look forward to questions. And thank you.
Before we move on, I just wanted to your work focuses on quantum information devices. And, as I was preparing for this panel, as I've talked to experts in quantum computing, they've talked about this idea that if you want to build effective quantum systems and networks, you need to go beyond the computers themselves and sort of rethink and redesign entire systems. Is the work you're doing right now potentially going to plug into that?
Absolutely. And what you're saying is true. What's important to understand is that the devices and the integration of devices in quantum systems is fundamentally different. That said, the integration of these with the strong silicon infrastructure in the US is a key important part of this. So we have a lot to build on, but it provides really a framework for great fundamental research that needs to be translated to manufacturable new materials and devices. And that's happening. So one of the things that I've been engaged with NSF is a workshop I'll hold at the end of May to focus on the key challenges in manufacturing these new devices, how to integrate them with silicon, our strong infrastructure, and build upon that.
And speaking of some of those manufacturing challenges, I'm going to go now to Daniel Holcomb from UMass, who's doing some really interesting work in manufacturing and manufacturing security. Daniel, over to you. Can you talk about your work a little bit?
Sure. Thanks, Rob. Good morning, everyone. So my work in computer engineering here at UMass focuses on design techniques for securing semiconductor hardware at a physical level. So this means that we're dealing with all kinds of supply channel issues, right? So things like keeping counterfeit parts out of systems, ensuring that chips don't leak information through side channels to the outside world, preventing untrusted foundries from being able to manipulate your parts in a targeted way, and so forth. All of these issues, I think, really relate to just the immense complexity of modern chips and the processes that create them. So these chips, have billions of transistors. They're created by large design teams split across locations and maybe across multiple companies. They're using design automation tools produced by yet other companies. And after all the design work is done, it's sent to a potentially offshore foundry to be fabricated. So every step in this process may have a different level of trust, And it's really just a huge attack surface that we have to defend. So our NSF-funded research in my group looks at the science of how to make secure chips in the presence of this huge and challenging attack surface.
Well, and I'd like to focus on that for just a second, because everyone I've spoken to preparing for this, everybody probably on the line has read about this issue of domestic fabrication versus foreign fabrication, and the idea that more domestic fabrication would be better. Your work seems to not necessarily taking, if domestic fabrication doesn't increase, your work seems to look at this idea of like if the present situation goes on as it is, how can we make it safer? Is that a fair way to characterize it?
Yeah, I think it's fair. We sort of play both sides of the issue. I think we certainly look at what can be done today to fix problems that exist, but this complicated process of creating chips, if fabrication capacity comes onshore and becomes more available to us, it certainly takes out one really challenging step in what we're trying to secure. There's still work to do. We'd have other things that we have to defend against, but it would certainly help.
Thank you. We're going to turn now to Malika Jeffries-L, who, when we spoke, you introduced yourself as being at the fringe of semiconductors, and I was hoping you can talk to us about that and what you're working on now.
Certainly. Good morning. Thank you for having me here, Robert. Yes, as I mentioned, my work is at the fringe, or we're kind of the stepchildren to the field. I'm Malika Jeffries-L, Department of Chemistry and Division of Material Science from Boston University. And I approach these problems from a chemistry perspective in that we are making organic semiconductors. So these are where we look at making carbon frameworks and to see if we can develop materials that will have semiconducting properties. And the biggest benefit of doing it this way is the tunability of the material. When you get into something that you can manipulate the chemical structures of, you can kind of do this atomic level engineering to build in the different types of properties you may need. And so we're excited to be in that area. The area is evolving. I think, back when it got started, people thought it was just going to be an academic curiosity, but now there's becoming real interest in developing technologies for commercial applications in solar energy conversion, in lighting, in display technologies and transistors. And so, we're just doing our part. My NSF-funded project is on developing new materials for use in organic light-emitting diodes, and we're happy to contribute to the science that way.
So your work focuses on these carbon-based materials, and as I understand it, there was a previous push to commercialize that, and it seemed to fall off a bit. So there's renewed interest. What's pushing it right now?
Well, I think the previous push was kind of one of these, these situations when the money people get involved and, the venture capitalists and people who are funding it for commercialization kind of set this deadline. You guys will get efficiency level silicon by this deadline, or this is dead. It's not going to happen. And when the science didn't get there by this predetermined financial deadline, people kind of gave up on it. But the researchers kept going in the labs. And then it's like, oh, wait, few years later, all of a sudden, these great results are coming out of academic labs, and academic industry partnerships are starting to push the products forward. And people are realizing, wait, we gave up. I think they kind of gave up on it a little bit it peaked late, and I think people gave up on it a little bit too soon. But on one example on the solar energy conversion side, when organic solar cells got started, we were getting fractions of percentages, a percent of the light that was incident to the device was being converted. And now, double digits was the goal. And now, people saying, could it get to 20%? It was a dream once to get to 10%. And so people are starting to think maybe there's something to this. And one of the other panelists mentioned this earlier, we can't also ignore the supply and demand issue. As there is increasing demand for semiconductors, we have to think about our supplies in terms of materials. The ability to solution process the material is a huge boon in terms of making large areas and large amounts of displays. It may also be the trick to getting around some of these limitations with Moore's law. And also, lastly, because these films we make organic devices based on thin films of materials, the amount of material that you actually need to cover a large surface, you're talking about, a meter of coverage with like a gram of material. And so there's some real benefits there. And I think people are circling back around to take another look. The other side, look at the US picture, it was kind of where I said people gave up. It was kind of here. The other countries kept going. And so we've got some catching up to do.
Great. So I'm going to turn to Subhashis Mitra, who is looking at, as I understand it, sort of a systems approach to semiconductors. Can you tell us a little bit about that?
Sure. Thank you, Rob. And good morning, everybody. It's an honor to be here. Before even I get into what I work on, let me thank the NSF, especially the SIZE division of NSF, for sponsoring my research, and obviously other sponsors and students and collaborators worldwide, without whom I wouldn't have been able to do this work. So I kind of work along two directions. The first of all, what I call nanosystems, as Dr. Tilbury and Dr. Martinosi mentioned, that progress in hardware technologies is absolutely essential moving forward, but at the same time, conventional ways of advancing hardware technology that we pursued for the past 50, 60 years have begun to stall at this exact moment when applications such as AI and communications and so on are demanding the largest improvements. So in that domain of nanosystems, my research is making progress around two essential axes. One is beyond silicon nanotechnologies, and the second is how do we build new three-dimensional nanosystems that exploit these unique properties of these nanotechnologies for significant performance benefits at the scale of 1000x. So that's like one of the areas of my research. And the other aspect of my research is how do you ensure robustness of future systems? As Daniel mentioned, when he was talking about his research, that robustness is a major challenge as systems become more complex, more interconnected, and more pervasive. Just think about a future chip that's implanted in somebody's brain and that chip is crashing. So hardware failures are especially a growing concern because chips are so complicated that existing ways of screening for design bugs and manufacturing defects hardly cope with existing complexity. And in addition, as we move to smaller feature sizes and more advanced technologies, somebody mentioned heterogeneous integration. Several reliability failure mechanisms that were largely benign in the past are becoming visible at the system level. And these barriers appear at a time when robust computing is more essential than ever. Think of from self-driving cars all the way to cloud data centers and supercomputers. So in this area, my research is creating new solutions that are already impacting actual industrial products in major ways.
Great. And so you actually, Tom mentioned NSF workshops. You recently organized one of them, and I know the report is forthcoming. But can you tell us a bit, when you get together with all these stakeholders and experts, a bit of what you took from that workshop?
Thank you very much, Rob. First of all, I have to say I co-organized this workshop with other colleagues. I was not the only organizer. And of course, NSF sponsored the workshop. The workshop actually focused on three major areas. The first one was on foundational nanotechnologies, and as I said, nanosystems. The second aspect was design enablement and electronic design automation for future generations of nanosystems. And the third area was how do we get access to foundries and hardware prototyping facilities to actually build and demonstrate these nanosystems and their unique capabilities in actual hardware. So those were the focus areas, and the key learnings were, I could just very quickly, tell you a few. Of course, recognition of the fact that future advances in nanosystems are absolutely essential for AI and communications and quantum and so on. But here is a really important aspect, which is that the field of nanosystems is very rich. And many promising research ideas can advance computing significantly from devices all the way to systems. So this perception that some people have that because our traditional miniaturization of transistors, that's slowing down, that does not necessarily mean that hardware technologies are slowing down. There are several other knobs, for example, three-dimensional integration and others that one can play to advance hardware technologies moving forward. And another really important aspect that was emphasized was this notion of cross-layer going from nanotechnology devices, hardware circuits and architecture to software and applications. There are a few other points that were made that relate to kind of research advances. where, for example, NSF SAIS, given their interests in software and hardware foundations, can play a very important role in kind of connecting these two worlds, the worlds of nanotechnologies with the world of actual systems and large-scale applications such as AI and others. And very importantly, education and workforce. That's super important because we need to attract the high school and the undergraduate students critically to this field to make real progress and lower the entry barrier and shorten their learning curves. For example, to access advanced technologies, there are export control concerns. How do you get access to prototyping and so on? I can get into some of those details later.
Great. So I'm going to, before we get to our final panelists, I'm going to remind reporters, if you would like to ask a question, please just type that question out in the Q&A box at the bottom of your Zoom screen. Also, if you just prefer to ask a question verbally, just note that and we'll unmute you to speak. We now have Joan Redwing, and honestly, I love the group that you're representing, the Two-Dimensional Crystal Consortium, which I feel like should get the prize for naming. Could you talk to us about the work you're doing?
Sure. Yeah. Thank you, Rob. And good morning, everybody. So I'm delighted to be part of this panel. And I also want to thank the reporters who are joining us today and taking your time to cover this important project. So my name is Joan Redwing. I'm a faculty member in material science and engineering at Penn State University. And as Rob mentioned, I serve as director of a user facility that we have. It's called the Two-Dimensional Crystal Consortium. So it's funded by the National Science Foundation. It's part of the NSF Materials Innovation Platform program. So the focus of our facility is on advancing the development of two-dimensional materials and devices. So two-dimensional materials, which includes two-dimensional semiconductors, really represent the ultimate scaling limit in layer thickness for devices. So they're only maybe an atom thick or a few atoms thick, and they crystallize in sheets. And the sheets are transparent, they're air stable, they're flexible. And so it's possible to design new types of devices and new device architectures by stacking the sheets one on top of another, or maybe integrating them with existing silicon devices and circuits, or by even twisting them to get new functionalities. So our facility is focused on advancing the synthesis and processing of these two-dimensional materials. So we're focused on being able to fabricate two-dimensional materials that are that have very high crystalline perfection over large areas, that would be suitable for integrating into devices and systems. And these materials can be used in integrated circuits, so more than more type applications where you're now stacking an additional layer of devices on top of your integrated circuit. Also flexible electronics, applications in Internet of Things, just connecting up, the devices that we use in our daily lives. And also there are applications in quantum technologies.
Thank you. And I was just actually going to ask you about we've talked about the focus of manufacturing, and how important your work actually involves this sort of like large sheet manufacturing. That's one of the challenges, is to figure out how to get there. When you're at the research stage in this area with semiconductors, how important is it to start integrating the idea of how can we manufacture this early into the process?
Yeah, I think with any new technology, it's really important to assess manufacturability early in the development stage. Even when people are doing research, if something looks particularly promising, you want to start thinking about the cost to manufacturing, the potential roadblocks that may exist. That's particularly important if you want to accelerate the transition of technology from research to commercial applications.
And so we actually have a couple of questions in the Q&A queue. Before we get there, just one thing I want to follow up on a point that was made earlier. So we have people on this panel representing different areas of potential development in semiconductors. And when you read sort of the press release about this, it's always sort of like this could be the next big thing. And so I'd like to put to the group, including our NSF panelists, how do these next big things, how can they interact? Are we saying it's an all or nothing game, or are these potentially technologies that could be integrated into current silicon systems? Different technologies may benefit different areas of computing or semiconductor manufacturing. How do you see this working in the next several decades as far as emerging technology goes? And open to anyone.
I can take it because we are doing it, Rob. So for example, our group has been working on carbon nanotube transistors and new memory technologies such as resistive RAM and their dense monolithic three-dimensional integration. And what is really important are two aspects. First of all, that these things are manufacturable in an actual silicon foundries, right? So that you don't have to throw away existing infrastructure to be able to do this. And the second point is it can integrate with silicon itself, because silicon is like what I call is rice or pasta. And on top of that, you put the sauce, basically, right? And that's what's going to happen moving forward. And we have been very fortunate that, first of all, NSF funded a lot of this research when we started. And then DARPA picked it up. And this is called the 3D SoC program. I think it's a major DARPA program, like over $60 million, 60. And Skywater Technology Foundry, which is a US foundry in Minnesota. And that's where the carbon nanotube transistors, the resistive RAM, and monolithic 3D has been implemented already, and it's working in actual silicon foundry. So your point is spot on.
Anyone else? I know some of our researchers have notes about how their technology would. Sorry, April.
Just to add to that, because I think it's important to realize that the infrastructure we have now is something to be built upon. So if you look at my areas of focus when I'm talking about quantum systems, which are really quite different, there's a lot of work to build hybrid systems and to understand how the systems level approaches, architectures are built together, all the way back to devices and materials, integration with silicon. And what we have in everything we've advanced in that area is crucial. So this is not an abrupt shift, although it is if you look at the end goal. But there are a lot of steps to build upon what we have achieved, basically.
Anyone else from the panel before we move on to our next question?
I can just add a little bit for that, Rob. One of the things that we fund at NSF is the integration of new materials into existing platforms. And it's not just in the semiconductor area, but it's cross platforms in all sorts of industries. So this is a common theme. You don't want, as I think was previously just mentioned, you want to build upon the huge infrastructure that you've built up and the capitalization that's already been put into there. I think a lot of the research, certainly things that Joan talked about, could be integrated into existing platforms building on the silicon technologies or carbon nanotubes. And so one of the things that we would like to understand more is what is the processing that's involved? What is the new science that we have to involve to make this at cost and make it efficient and to get the best utilization of all these materials in these devices and systems?
Great. Well, so I'm going to turn to our first reporter question. It's from Sam Moore from IEEE. And the question is, how important are back-end of line active devices to future semiconductors? Anyone want to be the first to take a crack at this?
I do not want to grab airtime, but but I can go if you want, Rob.
Please go ahead.
Hi, Sam, by the way. So this 3D technology that I was talking about, like using carbon nanotubes and resistive RAM and monolithic three-dimensional integration, which is actually working in an actual silicon foundry, that's an example of back-end of line transistors. The carbon nanotube transistors you can build at a very low temperature, and that's why you can put it on the upper layers of a stack of a silicon chip, and that's so important because when you put memory or other compute elements on the upper layers, you have to be able to connect with them. And you want to be able to go and address the memory. You need memory controllers, you need network on a chip, and so on and so forth. So that's going to be super important, and carbon nanotubes are only one example of that. One could do that with 2D materials and other stuff, but moving forward, that would be extremely important. But as somebody else mentioned, all that has to be guided by new architectures. It's not just about when I have a bunch of devices and I just spray them on the upper layers. It's about what new architectures you can build and what benefits they would bring.
April, what would you have to add here?
Absolutely, I agree. I mean, and I think the most important thing I heard there was, again, this convergence or cooperative research, where if you think about quantum, you're talking about advances in new materials and devices. But that's going to be most efficient if we can do that with new architectures and what's required overall. So agree.
Great. Well, our next question is from Pete Singer from Semiconductor Digest. He's saying he's hearing that design technology co-optimization, DTCO, is critical to semiconductor manufacturing success moving forward, where the design and manufacturing concerns are balanced. Is there work at NSF that's looking at this? And so I'll first kick that to our NSF panelists and see programmatically if we have anything, and then open it to the group.
So Donna, I didn't know if Donna was going to jump in there, but so there's a lot of interest in in co-design of manufacturing process with the product in mind, and this isn't just specific to semiconductors. And a lot of this has been brought about by the integration of new data analytics into the system as well to optimize the manufacturing process, without having to do a lot of the trial and error or physical modeling that's been done before. So we have programs, we have a cyber manufacturing program, and we have other programs that look at optimization in manufacturing. But this is open to all types of technology, including semiconductor technologies.
Margaret?
Yeah, sure. I would echo what's already been said about the fact that there's different opportunities for co-design at different levels. So one level is between the device technologies and the manufacturing that fits with them. And then the other levels are between the device technologies and the computational architectures and software that rests on them. And so those kinds of tight interweavings are important. We have a range of cross-directorate efforts related to this. For example, in the area of advanced manufacturing and future manufacturing, that's a place where we've seen SAIS and ENG working together across that kind of a space. Thanks.
And Dawn?
No, I think it's been well said. NSF absolutely supports work in this area. We could do a portfolio search and see what has been done, but this is a hot area because as we optimize each thing, it doesn't necessarily optimize the whole stack or the interlayers. So there's huge opportunities to develop methods to optimize up and down the stack or within the manufacturing process. So I think it's a hot area. There's a lot of people working on it, and we're funding all the best proposals that we have the money to fund in those areas.
So Pete, if you want more detail, please follow up with us. We'll be able to get you, we'll be sure to get you more information. Anyone on the panel want to comment on that before we move on to the next question?
Just wanted to say, even the world of DTCO is moving to what is called STCO. And that's like really hard, which is system technology co-optimization. So, you take your end system and then the technology and how you co-optimize. And NSF is playing a big role there. I know of multiple funding they're giving.
Okay. And so first, anyone else? I think anyone? Okay. So we're going to move on to Mitch Ambrose from AIP. How does NSF funded research in this area complement DARPA's electronics resurgence initiative? So I'm going to do the same thing. I'm going to start with Margaret on the NSF side and then see if anybody else on the panel has anything to say.
Thanks, Mitch. That's a great question. So we partner extensively with DARPA, actually, in a range of different ways. So we have truly joint programs. So for example, real-time machine learning is an example of a program where DARPA has funded PIs, NSF has funded PIs. The solicitation was a joint process, and the PIs meet together. So that's an example. We're also in ongoing discussions with DARPA MTO, I2O, and elsewhere to sort of advance on these techniques. We see our sort of positions being related but distinct. Empirically speaking, what we often see happen is that NSF gives someone their first funding in a topic area, often when it seems a bit out there and is a bit visionary. And then once they get a few steps further into it to prove the viability, we'll sometimes see the DARPA programs that stand up at that point to really push it to the next step. And so we work with them in a range of ways, and we partner with them directly when we can. Thanks.
I think that's an interesting note about how when one agency acts, it has ripples through the other research funding agencies. Anyone on the panel have anything to add on that?
Again, I don't want to take up all the airtime, but
Please.
I actually do have two concrete examples. So one is, again, when I started my career as a faculty, NSF came and funded me on, this nanosystems work. This was in collaboration with Philip Wong at Stanford. And we started working on this carbon nanotubes and then this 3D and all that. And, thanks to NSF funding, we actually demonstrated, for example, the first carbon nanotube computer and so on. But then DARPA came around 2015, 2016 timeframe, and they started working with us. And they started this major 3D SoC program, which was about not only just demonstrations, but how do you implement in an actual commercial silicon foundry? And my former student, Max Schulaker at MIT now, he got funded by NSF through his studentship, and now he's actually the PI of the 3D SoC. Similarly, on my robust systems work, the work on design bugs, it actually kind of started with an NSF expeditions in computing program. And then the DARPA POSH, which is part of the 3D, which is part of ERI, picked up on that. So I'm very thankful, and exactly what Margaret said about this kind of, it start, with at the NSF and then kind of go to DARPA, that I have experienced that in a big way.
Great. So this next question, I'm going to open up to the entire panel. Please jump in. Much of the focus of today's manufacturing push is on computing, but is there enough emphasis on wide bandgap semiconductors? And that's coming from Sam Moore at IEEE. Anyone can jump in.
Well, this is April. I can say something about that. Tom mentioned the recent workshop that I participated in, Future of Semiconductors, that NSF held, which has been incredibly interesting, but a key focus was on continued work on widebandgap semiconductors. So if you look at, I think, across applications and into my area of focus in this conversation, in, for example, quantum devices, there is a real focus and an understanding that we have a lot of great work going on, and our understanding of where wide gaps can make continued advances in applications is growing. So yes.
So before we move on to the next question, I just wanted to ask a follow-up to that and bring some of our other panelists in. Right now we're talking about the issues directly in front, the manufacturing capability, some of the research questions about what can be done right now. I'd like to know, from a fundamental research perspective, how far is the work you're focusing on looking at? Are you looking at stuff that you're looking to revolutionize semiconductors right now, or are we also focused on 10, 20, 30 years down the road? And I'd open it up to any of our panelists and see how long-term is your thinking right now?
I guess I can chime in. So for two-dimensional materials, these are definitely materials that could impact applications 10 to 20 years down the road. There's still a lot of just basic research that needs to be done in order to identify, applications where they're going to have an impact, but then also just to develop the materials to the point where they could be used in manufacturing.
Anyone else?
I'll chime in.
Mhm.
I mean, our field is in its infancy, but if you look at the progression over just a short time period of the last 30 years, again, I mentioned, 30 years ago, it was all a dream. And you look at, where things are improving with the development of new organic semiconductor materials and their utility in the solar application, it's really had a nice steady uptick over the years. And, I think I'd love to see what happens. I'm pretty young, so I plan to be around to see what happens when we extrapolate this out for the next 20 years, but to also look at ways in which we can get into newer applications. Listening to you all talk about manufacturing, I think there's some opportunities, where we can get involved there. And also somebody asked a question about wide band gaps. We can't get to very wide band gap materials. That is one of the challenges with organic materials. It's very difficult to make an organic material with a very wide intrinsic band gap that's stable. So we can't really do the UV as well for the LEDs, but we can do the blue, which is a hot topic area as well. So I think we're just getting started. I think the outlook is bright for the next 20 years.
Anyone else? Daniel, would you have any perspective on that?
Yeah, so, as the security person here, I probably don't look as far out as some of the other panelists. I think the technology has to mature a little bit to the point where, the processes are known and understood, and then we can find the vulnerabilities and then look at how to fix them. So if we look too far ahead, I think we're too speculative for security.
Okay. Subhashish?
Sure. I can, share a little perspective, and then I'll make a funny comment, but it's not funny. So, when you look at, kind of time horizons, I think we are always innovating. So even though we target something further out, there are immediate advances that also happen. And, I'll just give you, 3 examples at 3 time scales. I was talking about robustness. When I was at Intel, that time there was a major challenge with manufacturing. The cost of testing a transistor could be bigger than the cost of manufacturing it, for example. And I did something there called XCompact, and that was adopted within 3 years. And now, it's on every electronic system. If you take another extreme, right, which is my nanosystems work, it started in, as I said, 2006, 2007 timeframe. And now, after 15 years, you kind of see that, it's kind of getting there. Like a middle ground example is my work on reliability. Again, kind of in a 10-year time frame, you see things happening, in industrial products. But here is a really interesting one. We are professors, right? At least I'm a professor. So my products also include students, right? And our students, their timeframes are like 3 to 5 years, depending on whether they're a postdoc or they're PhD students. And they keep continuing. So I think our impact of our work kind of keeps going through our students and postdocs. That was going to be my kind of witty comment about this.
April, I don't want to leave you out before we move on.
Yeah,
Oh.
agreed. Nothing much to add.
Okay. Next question is from Pete Singer. Is there work underway in neuromorphic computing? And I'm going to turn to Margaret for our first comment on this.
Thanks, Pete. Yeah, that's an area of widespread interest. So we see it come up in different places across the NSF portfolio. Within SIZE, in our core programs, we have work on neuromorphic that shows up in the software hardware foundations area, architecture and the software side of it, and also in our foundations of emerging technology area inside the core. The other program that I'd want to note here, because it's really sort of a fascinating example of different types of partnerships, is the Collaborative Research in Computational Neuroscience, or CRCNS program, in which multiple directorates at NSF partner with multiple federal agencies. DOE just joined us this year, specifically looking at neuromorphic in that space. And so CRCNS started out with sort of putting computational ways of doing research into the neuroscience community. But as it has matured as a program, what we've seen is this really bi-directional flow of ideas back and forth from neuroscience into computing and vice versa. It's fascinating. The other thing about CRCNS is that this is an example of an international collaboration. There's on the order of 8 different countries that collaborate on CRCNS proposals. Thanks.
Anyone else want to jump in on neuromorphic computing?
I'll just jump in quickly, because one of the opportunities we see in neuromorphic computing is that the brain uses much less energy for computation than this current devices that we have. So we have a program in engineering called E2CDA, or Energy Efficient Computing from Devices to Architecture, and several of the projects within that program are looking at Neuromorphic as a way to save energy in computation. And of course, there are many other examples across NSF, but I think it is an ideal, right? The brain is incredibly energy efficient. If we could engineer devices that were as energy efficient as the brain, perhaps using neuromorphic computing, we would save a lot of energy.
And I think that's also one of the points a lot of our panelists have made is the energy consumption issue is another big question out there on semiconductors. So I just want to remind our reporters on the line that we're coming up on just 9 minutes left on the panel. We have a few questions in the queue. If you haven't gotten a chance to ask a question, please get it in now, because we're probably only going to have time for a couple of more. Right now, I am going to turn to Mitch Ambrose, who is asking, to what extent does NSF fund joint semiconductor research projects between universities and private companies?
So I'll start and say yes, all the time. There are many different avenues that we fund joint research between universities and industry. We have a GOLI program within NSF where the PI is a university and the co-PI is an industry, and they submit a joint research project to do the research together, and they need to have an IP agreement. We also have several programs that foster collaborations between university and industry, engineering research centers, several of which are focused on semiconductors or semiconductor manufacturing, industry university cooperative research centers that again bring together industries and government agencies and universities to do pre-competitive basic research in this center environment. And of course, we have the SBIR program that funds small companies, many of whom spin out of universities, to do translational research. It looks like Margaret is want to chime in and add some more, because we absolutely fund joint research with industry and universities all the time, especially in this space. It's important.
Margaret, please.
Sure. Dawn gave a great list. I'll just add to it that SAIS has done a set of direct partnerships with different industry entities in the semiconductor space. So we've had several program partnerships with Intel over the years, including in this kind of area. We also have done partnerships with SRC, the Semiconductor Research Corporation. And most recently, we have a program that's a bit more multi-layered, not just semiconductor focused, but across the layers looking at sustainable computing as a partnership with VMware. And so that's a real interesting example of how these semiconductor issues are, as I mentioned, creating a seismic shift that goes across layers. And so, yes, semiconductor vendors are interested in it, but other sort of cloud-based vendors are interested in partnering on this as well. Thanks.
Anyone else on that question?
I just wanted to add a slightly different perspective. You talked about the workshop that I co-organized, Rob. And one of the recommendations for the workshop, and our NSF colleagues haven't seen the final report yet, is that, you know, in addition to what NSF is doing, for example, co-sponsoring research projects, the idea was that moving forward for translational kind of projects, maybe NSF could think about actually even funding some industrial projects in collaboration with the clause that they would collaborate with certain academics on certain, you know, research topics. And that could actually create very bidirectional flow of information. And this was something that was recommended. And it's a different twist to the answers that we heard today.
Next up, and this is probably going to be our last question, I'm just going to tell reporters that, you know, we're looking at this as sort of being an opening. This is obviously a very big topic. If you have any further questions, please contact NSF. You're welcome to contact any of our panelists. And so Sam Moore saying, chip design, especially using advanced processes, is very expensive. And oops, sorry, I lost the end of that there. Give me just a second. Sorry, chip design, especially using advanced processes, is very expensive. Will making design chain more secure add expense? Is the research in this area aimed at keeping that cost down too? And I'm just going to add my own follow-up to that. After we address security, if any of our panelists, the work you're doing could address cost of manufacture, I'd love to hear from you after we address the security issue. So Dan, since this is security focused, let's start with you.
Sure. You know, short answer is yes. anything that we're going to do that's going to make chips more secure is going to have some cost, and certainly we want to keep that down as much as possible. When we're talking about getting your chips fabricated by an entity that you don't trust, that can be really expensive. To make this work, you have to withhold some information from the entity that's fabricating your chips, which means either that they're fabricating generic structures that you're going to then program, and generic structures are always more expensive than custom built, or it means that they're making let's say half your chip and then you're finishing the upper metal layers at another foundry that you trust. So we do want to keep costs down, but yes, there will be costs. If we can do more of our fabrication onshore, I think those costs can be brought down further.
Great. Subhashish?
Yeah, I could say a few words, so when it comes to security, for example, but in general, design bugs, when you talk about complexity in advanced processes, or even, side channel, security issues and so on. So there is a major need for new verification techniques, because you could leak information through IP, intellectual property, for example. And some of our work in that space, verification is a 30-40-year-old problem, but we have been able to make some inroads where instead of taking 12% months to verify stuff, we can do it in 2% days. So, new ideas are possible. And here, I don't want to put Margaret on the spot. She has done really great work, as part of her wearing her research hat on new ways of security verification, for example. So a lot of real cool stuff is happening in that space to bring the cost of design down.
Margaret, do you have anything to add on that?
Well, thanks for the plug, Subhashish, with my research hat on. Switching back to my NSF hat. Again, it gets to this notion of the seismic shift, that if we can think about these things earlier and not wait until we're at the fabrication point, we do have some opportunity and some leverage. So for example, we have a program called Formal Methods in the Field that seeks to take advances in formal methods, including verification advances, and see how to sort of push them out into real usages. And so some of that can be about security verification that crosses the hardware-software interface, for example. Thanks.
Great. Well, and again, I know we have short time left, but I'd like to turn that to the panel. Are there any cost considerations that you're looking at in your research? Particularly, I know retooling manufacturing is always expensive to start, but are there long-term cost issues that any of your research might address? No? Okay. Well, in that case, we are just about a minute out. And so I'd like to thank all of our panelists for joining us. This has been great. Thank you for taking the time. Thank you for joining us virtually. I know this is a new world of media briefings. I'd like to actually turn this over to our NSF panelists to see if they just have any closing remarks to our guests. Because I know these are people they deal with often.
I would just
Oh, go ahead, Dawn.
Echo the thank you for joining us. I think this has been a great panel, and hopefully it's just the start of the conversation to help us convey the exciting results that are coming out of NSF-funded research in collaboration with industry, in collaboration with other government agencies for advancing the frontiers in this very important area of semiconductors.
Great. Well, Margaret?
Just a big +1. Thanks to the panelists and to the many folks that aren't on this panel who could have also spoken. We'd be happy to have the journalists follow up for more names as well. Thank you.
And reporters on the line will be sending you more names. This meeting has been recorded. This will be available to you. Please let us know if you have any more questions about semiconductor devices, semiconductor materials, and we will close out there. Thank you all for your time.
Thank you for the opportunity.
Thank you.